Welcome. In this explainer, we're going to pull back the curtain on the invisible science that literally holds our world together. We're talking about the equilibrium of a particle. It's a simple but super powerful principle that keeps bridges standing and skyscrapers from falling.
I mean, have you ever looked at a massive crane like this one, lifting a load that weighs tons, and just wondered, how? Why doesn't the whole thing just buckle and collapse? How does it stay so perfectly still?
Well, the answer isn't magic. It's physics. The secret is a fundamental principle, a state of perfect balance that we call equilibrium.
Okay, to really get this, let's try a little thought experiment. Imagine you're trying to hold a balloon perfectly still, right in midair, but there are a bunch of fans blowing on it from all different directions. That one moment of perfect stillness, where the push from every single fan is perfectly canceled out by another, well, that's equilibrium. It's the point where all the pushes and pulls, what physicists call forces, add up to absolutely nothing, a net force of zero. And in the language of physics, this whole idea, this whole concept, is captured by one beautiful, simple, and incredibly powerful equation. It comes straight from Newton's first law, the sum of all forces, that's sigma F, equals zero. This right here, this is the bedrock of all stability. But how do engineers actually use that simple rule to design something as complicated as a bridge? I mean, how can they be so sure that all those invisible forces really do add up to zero? They start with a tool that is absolutely essential. It's called a free body diagram, or FBD for short. And let me be clear, this isn't just a helpful hint. You literally can't solve these problems without it. It's the crucial first step. All right, let's get practical. Take a look at this real-world situation, a simple metal ring being pulled by 3 different cables. This is a perfect example of a bunch of forces all meeting at a single point. So, to analyze this thing, the very first thing we do is mentally cut the ring free from everything around it. We're going to treat it as a particle, which, in physics is just a fancy way of saying we're simplifying it down to a single point where all the forces meet. And that right there is the key that makes even super complex problems solvable. Then we just draw that single point and we add arrows to represent every single force acting on it. And there it is. This simple sketch, this little map of forces, this is the free body diagram. It makes the invisible totally visible. And this diagram becomes our blueprint. It helps us account for all the different kinds of forces, right? Whether it's the pulling tension from a cable, the push from a spring, or that perpendicular force you get from a surface pushing back. Okay, so let's dive into this and see exactly how the FBD lets us apply our one simple rule of balance. We'll start in 2 dimensions. So on a flat plane, like a drawing on a piece of paper, our master equation, sigma F equals 0, splits into 2 separate, really simple checks. We just have to make sure all the forces balance out horizontally, that's the x direction, and vertically, the y direction. Now, what's so cool about this is how it shows the real power of that one rule. All it's really saying is that for something to be stable, every single force pulling to the right has to be perfectly canceled out by a force pulling to the left. And same thing for up and down. That's it. It's really that simple. So in any 2D problem, we have these 2 powerful equations. And if you remember your algebra, having 2 equations means we can solve for up to 2 unknown things, like say the tension in 2 different cables that are holding up a traffic light. This whole approach is fantastic for something simple and flat, but, we live in a 3D world, where forces can come from literally any direction, like on this really complex transmission tower. So let's jump into 3 dimensions, and you're going to see that the core idea stays just as simple and just as powerful. Now, to handle the real world, we just add a 3rd direction to our analysis. Along with the left-right x and the up-down y, we now have to think about front to back, which we call the z-axis. And what this shows so brilliantly is that we don't need some new complicated theory. The core idea is exactly the same. We just add one more equation to our toolkit to make sure the front to back forces also cancel out. And now, with 3 equations, we can solve for 3 unknowns. See? Same logic. So we've seen how this one simple rule applies in both 2D and 3D. But why is this so important? What's the really big takeaway here? It matters because these principles are the invisible foundation of our entire built world. They are the reason bridges stand firm against wind and traffic, why buildings don't just fall over, and why that massive crane can lift its huge load without tipping.
So the crucial point is that all of this boils down to a simple, repeatable, three-step procedure that engineers follow every single day. First, they set their directions, their axes. Then, they draw that critical free body diagram to actually see the forces. And finally, they apply that one simple rule, sigma F equals 0, to make sure their design is safe and stable.
You know, it is not an exaggeration to say that this one concept, sigma F equals 0, is the invisible blueprint that prevents complete chaos in our physical world. It dictates stability and structure literally everywhere you look.
And it's at work on you this very moment. The force of gravity is pulling you down, but the chair you're sitting on is pushing you up, holding you in perfect equilibrium. So just for a second, think about the constant, silent work of all the forces that are keeping your world in balance right now.